Hi, everybody. Welcome to our second lesson in our first unit. Today's lesson will be on theoretical probability. I think in our last video lesson, I wasn't aware that I had my a little picture-in-picture of myself in the bottom right corner as I was recording. It might have covered up one or two minor things, but I think you guys were able to get the content. I think I fixed that for this one, but we'll see when we get the finished product. So here we go. Let's dive in. Today we're looking more at theoretical probability in a bit more detail than we did yesterday. So we're going to start off with a bit of a motivation problem. So I myself enjoy the game Settlers of Catan. Maybe you've played it, maybe not. But I'm sure that if you think about it, you've played a board game that requires you to roll two dice and kind of get the total. In Settlers of Catan, you place your settlements around little corners of the. Let me go back there. Little corners of the game board, and when that number is rolled, you get resources. So, for example, let's say I had a settlement here where I'm putting this green dot. If a 6 was rolled, I'd get this iron ore resource. If a 5 was rolled, that's like pasture, I'd get some sheep. And if 3 was rolled, it's like a quarry, I'd get some brick. And you want to be placed on spots that get you a lot of resources. So on totals that are rolled more often than not. And so a good knowledge of probability will help you in games like Settlers of Catan. So we're going to analyze rolling two dice in a bit more detail right now. So here I've shown you all the different possible ways that you can roll two dice. So like the red dice is like the first roll or the first dice, and then the white one is like the second dice. You always have two. So you can see if looking at this first row, if the first dice is a 1, there's 6 options for the second dice. It can be 1 through 6. And if the first dice is a 2, then there's 6 options for the second dice, and so on and so forth. So you can see that there are 36 possible outcomes for the case of the event of rolling two dice. The number of elements in the sample space for rolling two dice is 36. Now, this doesn't mean there's 36 different totals. There's actually only, if we talk about what I might just erase that there. If we talk about what possible totals there are, you can get a total of 2 and a total of 3. And the highest total you can get is 12. There's only 11 totals altogether that are possible, but some are more likely than others. So that's a real important note. There are 11 possible totals, 2 through 12, but there's 36 elements in the sample space, different combinations of the two dice. So we're going to use that information to solve a few basic problems for rolling two dice. So you guys have that diagram. If you want to take a moment and give it a try. See if you can state all these probabilities. They will all be initially out of 36 before you reduce them if you'd like. So I'll do the first one with you, and then maybe you can pause, give it a try. So I'm looking at how many ways can I roll a total of 2? Well, the only way to do that is if the first dice is 1 and the second dice is 1. So the probability of rolling a 2 is 1 out of 36. Maybe I'll do the next one too. For rolling a 3, well, how many ways can that happen? Well, I can have a 1 and a 2 or a 2 and a 1. There's 2 ways out of 36. If you'd like, you could write that in lowest terms, 1 over 18. But I'm pretty relaxed in that regard there. For our purposes here, 2 out of 36 would be just fine. So why don't you try the remaining ones? You can pause the video and then pick it back up in a second. All right, so I will complete the rest. If you look at 4, there are 3 options of the 36. 4 of those options give you a total of 5. 5 of them give you a total of 6. 6 give you a total of 7, and then it actually works its way back down again. 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. And there's some symmetry there. 2 and 12 are rolled the least often, right? Only one time of the 36, whereas it is a 7 that is most likely to be rolled. So our answer to our second question here, a total of 7 is the most likely. And we got, visualizing that, there are 6 options here. The probability of rolling a 7 was 6 out of 36, or in lowest terms, if you like, that's 1 out of 6. Every 1 out of 6 times you roll, you expect to get a total of 7. And that's the unique total that gets rolled most often. Which total gets rolled least often? Well, it's a tie. It's a tie between 2 and 12. Probability of rolling a 2, there was only one way that happened out of the 36 possibilities, and that's the same as the probability of rolling a total of 12. You had to get 6 and 6. It's a unique combination. We can do some more complicated ones. Maybe you're playing a game where you get a bonus for rolling a double-digit number. So in this case, how many of our outcomes give you a total of 10 or more? And you can see that there's 6 of them. So the probability of getting greater than or equal to 10. As we can see, we listed all the outcomes so we can see them, 6 out of 36, or if you'd like, 1 out of 6. One last one. How about the probability that we roll an even number? So I might write this one this way, and you can feel free to as well. For getting an even number, well, that would be rolling a 2, and we're going to add up all the probabilities where we get an even number. So just going at this one in a slightly different way. Like you can certainly just count up all of the outcomes that are even, but we can do it this way too. So we had a 1 in 36 chance getting 2, 3 in 36. This is why it kind of is helpful to leave them at a 36. We had a 5 out of 36 chance for 6. Same with 8, and it is symmetric, 3 to get 10, and there was only one way to get 12. So by leaving them at a 36, it actually makes it a lot easier to add those up, and you can see you get 18 out of 36, which is actually 50%. So this is kind of interesting because if you list all the different totals you can get on a pair of dice, 1, 2, 3, 4, 5, 6 of those totals are even, but only 5 of them are odd. So an observer who doesn't know a lot about probability might say, oh, well, there's more totals that are even, so I should have a higher chance of rolling an even total. But because the probabilities are not distributed evenly, different things have a higher probability than others. It turns out there actually is just a 50% chance of getting an even total. Let's just talk about one more thing with this question. Let's say in a particular game, a total of 4 has come up only once in 20 rolls. So a player playing Settlers of Catan maybe says, man, this is I'm having terrible luck. I've only got a total of 4 once in 20 rolls. So we can actually tell our friend if they have a point, or if maybe they don't have a point, maybe they just don't understand. So 1 in 20, so to make a comparison, 1 in 20, let's maybe make that as a percentage. So divide and multiply by 100. That's equivalent to 5%. If you go back to our table, we analyzed the probability of rolling a total of 4, and it was 3 out of 36, which is equal to 1 out of 12. Or if you'd like to get that as a percentage to make the comparison easier, that's about 8.3%. So our friend in any given game can expect, 8.3% of the time to get a total of 4. Or looking at this, 1 in 12, 1 in every 12 rolls we expect would be a 4. In this particular game, this is what happened. Only 5% of the time did 4s come up. So I think our friend probably has a bit of a point. Their luck is not as good as what is expected. She expects to get 4s about 8.3% of the time, but they only come up 5% of the time. That's the thing with theoretical probability. It's what should happen, what we expect to happen, but of course, it's not always guaranteed to happen that way in real life. All right. So in the dice example, I'm just going to flip back through here for a big diagram. So when we wanted to, because the key to finding out all these probabilities was to see how many elements are in the sample space. In this case, it was 36. So all of our probabilities were at a 36. To find that out, we needed a diagram like this, some kind of organizational tool. So here we just drew a diagram and listed all the possible outcomes. There they are, all of 36. But what about this question here? What about this scenario? So imagine taking 3 coins in your hand and flipping them all at once. Or in a similar way, flipping a coin 3 times in a row and recording the result. How many different possible outcomes are for this experiment? Well, another way to do these kind of problems or to illustrate all the outcomes is by drawing a tree diagram. So I'm going to draw mine this way. For the first coin, I hope you all would agree that for the first coin, you could get heads or tails. For the second coin, you could also get heads or tails, but each time we add a coin, we're going to branch off. So if the first coin was heads, the second coin could be heads or tails. The first coin was tails, the second coin could be heads or tails. So you can see if you flip 2 coins, there's 4 possibilities. It could be heads, heads then tails, tails then heads, or 2 tails in a row. And we're going to add one more layer to this. When you flip the third coin, you've got to branch off one more time. Each of these options, you can get heads or tails. Heads or tails. Heads or tails. Now, in this particular question, we only have 2 little branches coming off each one because you can only get heads or tails. But if this was rolling a dice, we would have to branch off 6 times for each of the different, for example, like if the first roll was a 1, for the second roll, 2, 3, 4, 5, 6, you'd have to branch off. So you don't have to have just 2. You can have more branches like that. So now we can actually see how many possible outcomes are there. Well, how many different endings these branches are there? There's 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes. The number of different ways that you can flip 3 coins is 8. So you can see, you can even list them all if you want. You can get heads, then heads, then heads. Or we're kind of working left to right here. You can get heads, then tails. So that was that branch. And this is this branch here. The final branch would be tails, tails, tails. But hopefully you're convinced there's 8 different possibilities. So now we can actually answer some questions based on flipping 3 coins. So the probability of flipping 0 heads, 1 head, 2 head, or 3 heads. Refer to the diagram. The number of branches where you have no heads, there's only 1, right? It's when all of the coins are tails. So the probability of getting 0 heads, well, there's only one way that can happen out of the 8 in our sample space. It's 1 out of 8. In the same way, the probability of flipping 3 heads is 1 out of 8. There's some symmetry there. Flipping 3 heads is the right-hand branch. There's only one way that can happen. But then if you look, there are several different ways to get exactly 1 head. You could have the head, so you could either count them on the tree diagram or just list them here. But you can get heads and tails, or tails and tails, or the heads can be the last one. There's 3 out of those 8 that give you only 1 head. And finishing it off, there's 3 of those 8 branches left that give you 2 heads. You could have heads, heads, tails, heads, tails, heads, or tails, heads, heads. So a tree diagram is another great way to visualize all the outcomes and to see how many elements are in your sample space. Here it was 8. All right, so I want you guys to try this one. Maybe pause the video and give these 3 questions a try. Unpause them when you want to take something up. But baby Bryden is getting dressed to go outside, and so he has 3 different options for a blanket, blue, green, and white, and only 2 options for a warm hat, blue and white. So it's unlike the coin question, because here there's 3 options for his blanket, not just 2. So I want you guys to try drawing a tree diagram that illustrates these outcomes. So give it a try, see what you come up with, unpause the video when you want to check it out. All right, I'm going to continue. So for Bryden's blanket, we can have blue, green, or white. And then we need, for the next layer of a tree diagram, we will have branching out options for his hat, which can be blue or white. If he has a green blanket, he can have a blue or white hat. And if he has a white blanket, he can have a blue or white hat. So we can see that there are 6 different outcomes in this situation. The number of elements in the sample space would be 6. So let's just play around with that, do a couple things. So, there's the tree diagram on the previous, so you can ignore the previous or ignore this slide and just go look at the tree diagram on the previous one. The sample space. So I'm going to list the sample space here. So Bryden had 3 different options for his blanket and 2 for his hat. So it's not that difficult to list all those different possibilities. There are just 6. So I'm going to list it this way. For the blanket, it could be blue, and then the hat could be blue, or we could have had a blue blanket and a white hat, or a green blanket, blue hat, green blanket, white hat, and then finally a white blanket, blue hat, and a white blanket, white hat. So those are the 6 options. Again, number of elements in the sample space equal to 6. What's the probability that Bryden's blanket and hat are the same color? Well, we can now answer that. So the probability that they match, so maybe we'll do this one using our definition of theoretical probability. It's the number of different ways they can match all over the total number of possible outcomes, which we just found was 6. So you can go back to the tree diagram or where we listed the sample space, and you can see there are 2 outcomes where his blanket and hat match. They're both blue or they're both white. So probability of the same color is 2 out of 6 or 1 out of 3. Final question here. What is the probability that Bryden's blanket and hat are not the same color? So there's 2 ways you can go about this. So you can go back and just count all the outcomes where they're different, and you can see that there are 4. Or you can think of it this way. The number of ways to have no match, see, would be the total number of possible outfits for Bryden minus the number of outfits that match, because his outfits either match or they don't. There's only those 2 options, and we found 6 elements in the sample space. There are only 2 that match. That must mean there are 4 that don't match. So the probability of having no match would be 4 to 6, or 2/3. This brings us to something called the complement of an event. So here, the event having no match, his clothes not matching, was the complement of his close matching. Those two events complement each other. The formal definition of a complement is the following. So if an event is noted A, the complement, we use that little tick of the apostrophe above the A, and we read that as A prime. So for example, if event A is rolling a total of 4 on some dice, then the complement would be rolling anything other than a total of 4. And like for in this question here, if we call the event of matching M, then the complement of his close matching would be not matching, and we would call that M prime. But the thing with complements is that the probabilities have to add to 1, and that makes a lot of sense because either something happens or it doesn't. And when you add those two things up, it should encompass all the different possible outcomes. This gives you another way to find probabilities. If you're finding the probability of the complement of an event, this is just rearranging the previous equation there. You just subtract the probability of the event itself from 1. That's kind of what we did in the previous example. All right. The last thing I want to do is actually show you exactly how you can express a probability in terms of odds. So what I've given you here in this table is actually just a pair of, it's the same event. And in the first line, it gives the probability of that event happening. And in the second line, it tells you what the odds in favor of that event happening are. Maybe you want to pause the video here and see if you can see the rule. And then maybe you can predict what the odds of an event would be if the probability was, say, 2 out of 7. How would you express the odds for that? Pause the video, give it a try, and unpause when you're ready. All right, here we go. If you said the odds in favor of that event were 2 to 5, you'd be right. So in the first case, the 4 would go in the first slot there, and the 5 would come from doing 9 minus 4. So it's like 4 favorable outcomes, 5 unfavorable outcomes. The same rule happens with the second one. If the probability of an event happening is 3 out of 4, then every 4 times it would happen 3 times and not happen once. And the same rule holds for 1 out of 5. In 5 times, it would be successful 1 time, unsuccessful 4 times. So the odds in favor of an event are given by, we write it this way. It's the number of favorable outcomes to the number of unfavorable. Turning that into our set notation, turning that into math, the odds in favor of event A are given by the number of ways A can happen, the number of ways A can't happen, which is the number of ways that the complement of A happens. So it's that ratio, n of A to n of A prime. Sometimes we also might be interested in saying the odds against something happening are, and it's just simply the reverse of what we just did. The odds against an event are given by the number of ways it cannot happen to the number of ways it can happen, like so, just to flip. Let's try that out. Let's just do a couple examples with odds, and I'll give you guys your next steps after this lesson. So let's determine the odds in favor of the following. So your birthday falling on a weekend. So we have to think, well, how many successful outcomes are there here? Well, there's 2 days on the weekend, Saturday and Sunday. And we've got to be careful. It wouldn't be 2 to 7. Remember, it's the number of favorable outcomes to the number of unfavorable outcomes. The number of days that aren't a weekend are the weekdays. Monday through Friday, so they're 5 days. The odds of our birthday falling on a weekend would be 2 to 5. The probability would be 2 out of 7 of days, but the odds would be 2 to 5. Rolling a 1 on a single die. Well, there's one outcome that's a 1. There's 5 outcomes on a single die that aren't 1. So it'd be 1 to 5. And again, if the probability would be 1 out of 6, we know that. And you can see those line up using the rule we discussed earlier. Why don't you guys try the next two? So that should be D. And then see what you come up with. Unpause the video. We'll take these two up. All right, here we go. So on a single die, the number of successful outcomes to get an odd number, well, that could be 1, 3, or 5. So there's 3 different ways you can get an odd number. And then because there's 6 sides, that would mean 3 ways to get an even number. So we can put these odds in lowest terms like a fraction. We would say the odds are 1 to 1. So it's like even odds. And lastly, the odds of your first test falling on a Tuesday. So be careful with this one. There's one day that's Tuesday, but the number of unfavorable outcomes, so because you can't have a test on a Saturday, Sunday, it must be a weekday, right? So, one day is Tuesday, 4 of your school days are not Tuesday. So those are the odds of your first test coming on a Tuesday. All right, so as far as your next steps go, there is a short formative quiz online, very short, 5 questions. Just give it a try. It's, again, it cannot hurt your mark. It's purely formative. But if you do get 5 out of 5, it can help your mark. I'll record the mark, just weighted very little. I have a task for you. It's kind of like the 2 dice problem, tossing in a little bit of a tweak in there. I'll have you guys take a look at the SumSwamp task. You can, I think it would be best if you printed off the SumSwamp analysis task. It's a PDF. Print it off, do it, and then scan and submit in the Dropbox. I am open to other possibilities, but I think that is the easiest way to do it. And then if you want or need the extra practice, I've got a PDF of practice questions on theoretical probability that we posted onto our course. All right, so good luck with that. Let me know if you need any help, and look forward to talking to you guys and working with you guys again.